Hello, I'm Professor Leslie Rusch from Université Laval in Quebec City, Canada. Within that, I'm in the Center for Optics, Photonics, and Lasers and in the Optical Communications Laboratory. I'd like to thank the organizers of the conference for giving me this opportunity to talk to you about my research today. I'd also like to acknowledge my co-author, Professor Guan, who is formerly with us, but who is now a professor at Tsinghua campus in Shenzhen. So I'm going to start with the conclusion. Because I'm an academic, you can think of this as the thesis that I'm going to be defending during my talk today. So my first proposition is that 5G and 6G radio access networks, they require a smart edge where we locate high-performance computational equipment, and this will allow us to increase capacity and, of course, ultimately make more money for the network operators. It also requires remote units. These are the hardware units located right next to the antennas, and these remote units must be simple, low cost, and low energy. To meet these requirements for 5G and 6G radio access networks, we can turn to silicon photonics microwave technology. They're particularly appropriate because of their very small footprint and small energy consumption that allow them to scale to the large number of antennas that we see in 5G and 6G. These devices are compatible with analog radio over fiber, which is a solution that reduces latency and increases capacity. Of course, they're also compatible with digital radio over fiber, which can be used at very wide bandwidths. So in order to defend this thesis, I'm going to start out by talking to you about what the 5G, 6G requirements are and what challenges that they pose. That tells us why we're going to use radio access networks, and in particular radio access networks with a smart edge. And then I'll show you how we can use silicon photonic microring modulators in order to create a radio over fiber system within the radio access network. And finally, I'll show you some demonstrations, experimental demonstrations that we've made for these systems. So this diagram is a visualization that lets you know some of the key requirements, key performance metrics that we're looking for in 6G systems. And they vary across all kinds of parameters, from spectral efficiency to energy efficiency to data rates, density, etc. And within this diagram, so all that outer sort of stop sign sort of shape is for 6G, and within it we have a comparison with what the requirements were for 5G. And we can see that if we're going from 5G to 6G, we're pushing out in many different directions to improve performance of these systems. So where is it that optics comes in play? Where can optical communications contribute to meeting the requirements? And there are basically three target requirements where optical fronthaul comes into play. And they are, and certainly the capacity, the ultimate data rate that the user sees, the energy efficiency, and also the latency. So I'll be talking to you about how we can devise a solution in optical communications to help on these fronts. So let's start with the most basic cellular system, historically the approach that was used. So we start on the left with a base station here, and the base station is an antenna tower, and at the top of the tower we have the remote unit. That's the electronics that are really right next to the antenna. At the base of the tower we might have some more hardware, which is more easily accessible, which we'll call the central unit and the distributed unit, and especially the distributed unit is where the baseband digital signal processing is going on for these RF signals. So this split of responsibility is covered by the standard for 5G and 6G. Of course, from there, now we see where optics comes into this standard cellular approach. We have the backhaul, which is a fiber which connects the base station to the core network. And this, of course, is a completely digital link. One of the improvements that's been made over the years on this base station is to add some computational equipment close to the end user. This is called the MEC unit, and this is power located, computing power located at the tower, but this is really for applications, not for the RF signal. Now, because all of this equipment is really co-located with the antennas, there are no latency or bandwidth issues for the backhaul, especially since we have this MEC unit, which gives you the computational power for those applications which are latency sensitive. So they're latency sensitive, they're next to the unit, and so the backhaul only handles applications which are not latency sensitive. So this is the, let's say, pre-5G, pre-6G solution. However, this solution does require complex hardware here located remotely next to the antenna tower. And most importantly, there's no RF coordination that's available. And it's the RF coordination that is really going to let us meet the 5G and 6G requirements. So how do we go from this basic cellular approach to one that allows us to handle two things, dealing with complex hardware and also coming up with better RF coordination? And that leads us to this discussion of radio access networks, which is the way we're going to be able to meet these, especially with the smart edge. So when I talk about radio access networks, it's sort of inspired by the cloud paradigm. So if we look down here at this very simple informational graphic, we have a bunch of applications, things in the Internet of Things, which are mobile or somehow are communicating with this cellular network. But ultimately, some of the compute processing power is actually going on in the cloud. And this works very well for applications which are not latency sensitive. And of course, when they are latency sensitive, we want to bring some of that compute power over to what we call the edge. And this is where we call the edge of the network. So we would like these cellular antennas to somehow be connected so that we can do our coordination. And so it's not just the applications that are going to have compute power at the edge, but we're also going to take some of this RF coordination and try to have that also doing. So the RF coordination also requires high computing power, but we cannot go to the cloud for this computing power because the latency requirements on the RF coordinations are just too strict. So the cloud's too far. We can't push it to the mobile devices because their compute power is too limited. So we're looking at this Goldilocks solution, which is to put some intelligence at the edge of the network. So in the radio access network that we connect all of these RF units which are going to be coordinating, we need an optical fronthaul. So this optical fronthaul is the enabling edge computing. And I'm going to talk to you about some strategies for how we can implement that. Before I get to fronthaul, let's talk about the mid solution. And this is a solution which addresses the issue of hardware complexity. So in this case, our functional split that we're looking at is we leave the remote units up next to the antennas. We have the DU units, which are the baseband DSP, which are staying close to the RF signal. And now this MEC unit, we're pulling back a little bit, and all of the CU unit, which is basically a network level coordination, is being pulled back to the edge of the network. So this is allowing me to put some very complex hardware into a pooled capacity where I can reduce cost, easier to manage, easier to give maintenance, etc. So in this case, the mid-haul is an optical link, and there are no bandwidth issues because this is a completely digital, no radio over fiber, completely digital because all the radio signals are staying at the antenna tower. There are some latency requirements for the applications, which are being met by putting this compute power at the edge, the MEC. However, this does not have RF coordination. And for the RF coordination, these DUs, these baseband units, also have to be pulled back to the edge. And this is where we introduce the idea of fronthaul. So now I'm introducing RF coordination, and this is what is going to let me meet all of those really stringent performance metrics for the 5G and the 6G network. So we have pulled all of our functional split now is to only leave at the antenna tower right next to the antenna, the remote units. Now we have an optical link that pulls back these radio signals. So now this fronthaul has to handle radio over fiber so that the radio signals come to the smart edge. And at the smart edge, we're going to be doing the digital signal processing, the baseband that we always did traditionally. But in addition to that, we're going to have this coordination. So this COMP, this is the acronym used in the 5G standard, is where we're going to do this RF coordination. And of course, this coordination at the RF level with these mobile devices zinging along and these RF channels changing very quickly has very strict latency requirements, especially as we move on into the future into very advanced applications which are not just coordinating RF signals, but also perhaps doing control of autonomous vehicles, which have, again, very strict latency requirements. So these are the advantages of this for the fronthaul, but it also comes with some challenges. But first, let me talk about this RF coordination. What does it mean? What does this comp do? Just to give you a feeling for it. So if I only had one antenna connected to this smart edge, then the antenna would send this radio signal to the smart edge, and this this computational power at the smart edge would be able to actually do beamforming. So I have multiple antennas at the top of this antenna tower. Each one of them requires certain weightings in order to shape the beam towards the cellular unit. All this computation of the proper beamforming strategy could be done at this smart edge. Excuse me. We could also not only connect one antenna tower, but connect many antenna towers. Okay, now any given mobile device I can now support with multiple towers, which really allows me to do some constructive combining, really increase the signal quality, and this is going to let me, increase data rates, increase coverage, etc. And finally, I talked about beamforming, but now if I have information from many antenna towers, all of the RF signals, I can actually do shaping where I put reduce interference to some user in addition to strengthening the signal to another user. Okay, so all kinds of ways that if I use radio signals, I can get increased performance. But what I need is what we call a channel state information on the RF signals. So I already have the central controller, but what's needed is the radio over fiber that gets this channel state information, gets the RF signal into the smart edge. Okay, so now we can talk about how are we going to meet that radio over fiber requirement. So latency and fronthaul for the sort of minimal requirements for some of the baseband processing, simple baseband processing, less advanced ones, is for a return trip timing of something like 200 microseconds, which means that the fronthaul cannot be any longer than 20 kilometers. Of course, I could use some hollow core fiber and extend that range, but for standards as a single mode fiber. And if we get into some of the applications like in the 6G targets, they can be as severe as 10 microseconds. And in that case, we're going to limit the fronthaul. Really can just physically only be at most 1 kilometer. So having discussed, why it is we need a fronthaul, why it is that this fronthaul has to carry the radio signal over it, now we'll talk about how silicon photonic microring modulators are particularly appropriate and how we could use them. So first of all, remember I talked about the remote unit equipment high in the antenna tower, the distributed unit where the baseband digital signal processing is happening and that I have pulled into the smart edge. So I have to carry radio signals over the fiber. Do I want it in digital form or the native analog form? If I put it in the digital form, we have a standard known as CPRI or extended CPRI, eCPRI. It allows us to do, at the remote unit, we'll have, of course, our RF chain, our amplifier, whatever we need to go to the antenna. We'll also have to do an analog to digital conversion because I'm going to do digital radio over fiber, and then I convert from electrical to optical. Goes down my optical fronthaul, and at the DU, at the distribution unit, I have to convert from optical to electrical, and now go back to analog, so I have my RF signal, so I can extract from my RF signals coming from many antennas all the channel state information I need in order to do excellent baseband processing. Now the eCPRI standard has some legacy issues and is not very bandwidth efficient. In fact, it's sort of very high consumer of bandwidth, which is why if I go the digital route, it's very hard to support and to scale into a very large number of antennas, but people are working on this. And this is, I think, what we would call the standard solution. I'd like to talk today about another solution, which is to use analog radio over fiber. And basically, we get rid of this analog to digital conversion back and forth. Because of this, we don't have to use the eCPRI protocol. And because of that, it becomes more bandwidth efficient. But because we've eliminated some hardware, it also becomes more cost efficient, power efficient, and lower latency because we have less processing going on. So for either these solutions, digital or analog radio over fiber, I believe that silicon photonic microring modulators are an excellent solution. They're compatible with CMOS, so therefore, the cost for integration could be low. They're very compact. We'll be looking at units at something like a 20 micrometer radius for these microring modulators. And because of this compact footprint, they're also very power efficient on the order of milliwatts, and they're simple driving systems, signals. So let's start with in the core network, like if I were doing backhaul, for instance, I could use silicon microring modulators. For instance, I could use an IQ and do coherent detection if it was merited, with cascaded microring modulators in a Mach Zehnder configuration. Now, once I get from the core network into the smart edge, at the smart edge, I can also use microring modulators, and in this case, I would be putting on the RF signal. So this is when we're coming into the radio over fiber part. And we could do this WDM, of course, again. And ultimately, up at the remote units, I have to drop, separate perhaps many signals for different antennas. So I could use microring resonators in order to drop the signals, and I could use microring modulators, of course, to create the uplink for the return signals. So just to show you that these silicon microring modulators have a place all across this radio access network. So as I said, in the core network, we could use this IQ structure for coherent detection, which has high spectral efficiency and high capacity. The advantages of using a microwave modulator in this scenario would be for smaller footprint and lower power. And ultimately, with these 5G, 6G systems, it's power not only at the antenna system, but in the entire network that we're trying to improve. So we could eliminate the components of the AWG, so it's more compact also than the Mach Sender. So again, it's an efficient solution with the microwave modulator. Now, to come back to this idea of IQ microwave modulators, which can be used for coherent detection, they're very versatile. They could also be used for direct detection. And when I use direct detection, I would actually be using the IQ modulator to create a single sideband signal, for instance, with OFDM. And that is because these single sideband solutions are very robust to fading. So this could be used. Here we have this is of course, when I talk about fading, it's chromatic dispersion induced power fading, which is only really a problem when I have a double sideband system like I'm showing you here, because of, here is the dispersion in versus wavelength. And if I'm over in the C-band and I do have this double sideband, then I'm seeing different kinds of dispersion in the two sidebands. And if I eliminate one of them, then this sort of poor recombining at detection can be avoided, because on a single sideband, of course, the dispersion is fairly constant. So we have demonstrated this direct detection with what we call complex signaling, because I just use this Hilbert complex conjugate symmetry in order to suppress one of the sidebands. For instance, if I use double sideband, here's a spectrum after like 20 kilometers, how badly the dispersion has impacted. Whereas if I use single sideband, I get something that's very, very flat return and very good recovery. So at the Smart Edge, we could use cascaded microwave modulators. Here I'm showing just single modulator microrings, but of course they could be in the IQ configuration for single sideband if needed. But there's all kinds. One thing you'll notice is that I'm using a configuration which is a distributed carrier. So for direct detection, we need a carrier that is transmitted with the signal. And also, if we, of course, go into the distribution to all of these various antennas, we're going to need an arrayed waveguide grading to separate out maybe different wavelengths going to different antenna towers. And this AWG could also be implemented in silicon photonics. Finally, I'd like to point out that there are a variety of modulation formats that can be used for the radio over fiber. I mentioned one of them being the wideband OFDM. So it's sort of a digital radio over fiber with OFDM. So that would be this solution. We could also do analog radio over fiber, where here we have the sort of RF carrier is native here. And then we have analog radio over fiber and baseband. So this is much narrower band signal than the maybe very wideband digital ones. This is analog, more spectrally efficient. And of course, then at the antenna tower, it would have to be mixed up to whatever the RF carrier was. So variety of modulation formats, all of them compatible with the microwave modulator solution. Now, at the remote unit, I talked about how we're going to be able to strip off different antenna signals using microwave modulators. And this is very important with the idea of this distributed carrier as well. So I would have a cascaded ring of modulators that would be tuned to different wavelengths in order to drop particular signals. And again, I'm showing a variety of different kinds of signals that I could be dropping. So after all of these cascaded microwave resonators, what's left is I've dropped all the signals, but I have left a carrier, and a carrier is used now for remodulation. So now on the carrier, I can create an uplink, again, digital or analog radio over fiber, but no optical source is needed. So I'm keeping the the complexity, the size, the power consumption at the remote unit as simple as possible. Very important because these are very difficult to reach. You want them to be very robust. And now I'd like to just talk about some of the demonstrations that we have performed experimentally with this configuration. First, we're not the only group, of course, to work on this. There was some excellent work in Europe on the Horizon Fabulous program. And of course, there are many others, but I'll be talking today mostly about ours. And I mentioned already that we could use this IQ microring modulator configuration, or 2 microring modulators in a Mach-Zehnder configuration, in order to do single sideband modulation, for instance, for digital radio over fiber with very wideband OFDM signal, and we got 18 dB extinction ratio. And of course, I showed you that this was very effective already in combating fading. It's not just that the spectrum is tilted, but of course the constellation was unrecoverable, whereas we get very flat response and you get very highly recovered signals with this single sideband modulation. We've also looked at the smart edge, how to deal with analog radio over fiber. We've looked at these 2 methods on the native 5G 6G carrier and also in baseband. And we've done demonstrations where we've produced both kinds of signals, and we've also done this on WDM on multiple wavelengths, all using a cascaded microwave modulators. So we've in particular looked at this coexistence of heterogeneous WDM signals. So we have this very narrow band radio over fiber, then we've had this wider band. So these 2 can actually coexist very well also in the radio access network. We've looked at this carrier distribution, how we can share the carrier power in order to do very good detection, and how we can also use it, of course, to save some of the carrier for remodulation. And this graphic just shows, as we use different amounts of carrier, on the x-axis here, is as we're dropping different amounts of that carrier to do detection, and how good the error vector magnitude is, or the performance is. And of course, if we use all the carrier just to do detection, so that's on the sort of blue shaded area, we would use all of the power in our distributed laser just to do detection. We would have excellent performance. And if we used less power, there's also some decent performance we can get. And this is the trade-off. How do you deal with distributed carrier? We've done all 3 modulation types together also in our Clio paper. And just to say that whether we use very wideband OFDM or 5G radio over fiber, whether in passband, baseband, we're getting bit error rate performances which are quite acceptable. Finally, we also have looked at remodulation. After we have examined, how much power do we need for detection, how much of it can we conserve for remodulation, and here you can see that there is a very good extinction of the wideband signal OFDM in this case. Here, this little itty bitty carrier here is a little bit of residual radio over fiber from the downlink, but this large carrier has been used to remodulate the uplink. So in this case, we've done good detection, we've dropped these, and we've still got been able to uplink, modulate again for the uplink. So I'll end getting near the end here. Is it really that simple? And of course, I haven't talked about the challenges of using microring resonators and microring modulators. The stability is challenging, and of course, people are working on this constantly, and it's getting better and better. And these are thermal processes which are very slow, and so it does add complexity, but all of these solutions are integrable, and we don't believe it will add too much to footprint or power consumption. Polarization sensitivity in silicon photonics is also an issue, and I didn't have time to talk about all of it today, but there are various polarization diverse designs that we have come up with and that will help keep costs down because they're very efficient designs. So my conclusion, no longer an exclamation point because we expect it at this point, is that 5G radio access networks require a smart edge, and the smart edge requires RF information. Which means that we need radio over fiber. And also the remote units that are producing this radio over fiber signal should be very low cost. Silicon photonic microwave modulators are an excellent solution for this problem. And that is because they're small footprint, small energy, lots of antennas still works. So we've discussed analog and digital radio over fiber that can be using this technology. So finally, just thank you for your attention, and I'd like to acknowledge some of our partners in this research. Thank you.